Okay, maybe I can start. So, welcome to the second session of this talk. Today's the workshop, and I want to introduce another great speaker, Takaaki Hori, at MERL, Mitsubishi Electric Research Laboratory, and he has been actually working on the NTT for a long time and moved to MERL, and I actually have been working with him a very long time, and he's always produced amazing result when I was working with him. So some people actually called him magician. And today his talk is about end-to-end speech recognition in complete data scenarios. I am also working with him, and he also showed a lot of magic to you guys. So please enjoy.
Thank you, Shinji. Hello, everyone. I'm Takaaki from MERL. What I will talk today is mainly related to our activity this year's Jelinek summer workshop. We worked on this research topic very hard this summer. So I'd like to introduce some results from the outcomes of the workshop. As you may know, automatic speech recognition technology is now widely used in many applications, such as smartphone car navigation, and also recently getting much more popular, the smart speakers, something like that. Of course, building an ASR system is quite expensive and time-consuming. Because we need a lot of resources, experts. So we need various experts to build a ASR system. So we also need big data. And also, we need strong computation powers. So big companies providing the speech recognition services all have tons of this kind of resources. It's quite difficult to compete with such large companies for Mitsubishi, but but we still need to work to improve the recognition performance. Okay. For example, for experts, actually, expected to make algorithms. It's quite important to improve the performance. But recently, we can obtain the tons of technical papers and free software. This part is actually not so, still important, but not super difficult part, actually. I think it's important, for me. Okay, and also it's quite important to have a good pronunciation dictionary for speech recognition. This data is quite also crucial for speech recognition. So experts need to define good phoneme units and assign the correct pronunciation to each word. And typically, for some speech recognition tasks, the vocabulary size is roughly 200K words or something. So it's quite not so easy to make a good pronunciation dictionary. And for some languages, we also need some tokenization techniques, like for Japanese, Chinese, or Korean languages, and also G2P conversion or something like that. And difficult thing is that these expert knowledge is language dependent. So we need to, if we want to make ASR system for a new language, so we need to build this kind of data. And also, Yeah, big data. So data is also quite important. So to train ASR models, we need a paired speech and text data. Hopefully, we want to have more than 1,000 hours. So actually, so recently we can get tons of speech data or text data from internet or website, but the amount of paired data is still very small and difficult to collect such data. So we need to ask many people to read aloud text or transcribe audios. So, and moreover, so to support multiple languages, so it's also a big problem. The costs will increase much more. So SR system is language dependent. So cost for one SR times the number of languages will be roughly the total cost of the building such SR systems. So yeah, but so big companies trying to cover major languages. Yeah, it's good. So actually, Google already supports more than 100 major languages and dialects. Yeah, it's amazing. Yeah, but I think they don't care about low resource languages. So, and also, so you know that there are almost 7,000 languages in the world. So the question is, so how do we support more and more languages? So this is a problem. And this is main topic we pursued during the summer workshop. So to tackle with this problem, we submitted a proposal of this project named Multilingual End-to-End Speech Recognition for Incomplete Data. So we co-released this project with Shinji Watanabe. And so maybe I think you all maybe familiar with the Jelinek summer workshop. It's a kind of a hands-on workshop in speech and language processing, having 23 years of history since 1995. And this year, only 3 projects was accepted, including ours. And yeah, actually, we worked hard this summer to pursue this project. Okay. Fortunately, we could have very nice team members, including 27 people. So 4 senior members and some affiliate members. Also, PhD students worked very hard, so they are very helpful. And also some off-site members, including some Google people and some other students, PhD students in Japan. Yeah, actually they helped a lot through the discussion of each research topic. And also some students actually remotely was remotely working. Okay. So in this project, we worked mainly on the 2 research direction. So one is a low resource end-to-end ASR. So here we want to reduce the need for expert knowledge and big data. Where we investigated new model architecture and algorithms to improve performance in low resource scenarios. And also we worked on the kind of running algorithms for incomplete data. So here we want to reduce the cost for collecting paired data. So we explored a new method for training the end-to-end ASR models using unpaired data. Okay. So we consider in this project So different types of incomplete data scenarios according to the amount of the complete data. So here is some example. So, yeah, actually the amount of the data is really dependent on the language. So what language is built for the ASR? So for English, we already have tons of data, and we can get some over 1,000 hours of the data. But in some languages, we only have, it's difficult to find the data more than 100 hours. And also some very low resource languages, we cannot find any paired data, something like that. And we assume that, but in this project, we assume that some incomplete data are available. So for example, also unpaired data means audio-only data or text-only data for the target language. And also we can utilize the other language data, which are hopefully paired data. So, and so we want to reduce the error rate in all the scenarios in this workshop. Yeah, like this. So this is the goal of our project. But in this project, mainly, low resource part is mainly we worked on this workshop. Okay. So here is a real use case. So if we get built a nice technology, so this is so if we when we try to make ASR system for a new language, so we can collect the audio data from some TV show or something. So actually, we don't have the transcription for this audio data, but we can also collect the text data from website. And these data are in the same language, but not related. So this means unpaired data. So we try to train the end-to-end ASR model without expert knowledge. So it's, I think this is quite easy to make ASR system so with low cost. But actually, only using the paired data is quite difficult. So we assume that a small amount of transcript data is available. So actually, we had many results in the workshop, and I cannot explain all the results in this talk. So I will present some of our results from the workshops. So in summary, so in this project, we built a multilingual end-to-end ASR system for 17 languages, and we got some significant improvement with novel architecture and training methods. And also, we try to build end-to-end ASR TTS chain and unpaired data training methods. And also, we built our open source system named ESPNet in this project. Okay, so I'd like to present two topics from Jelinek workshop. So the first one is advanced end-to-end ASR architecture, including attention-based multi-encoder fusion approach, and the other is a look-ahead word-based RNN language model. And the other topic is a learning method for unpaired data. So here we applied the back translation approach and cycle consistency based training. Okay. So first one is done by these people called these team members. Okay. So yeah, I think so. Most of people already know about the end-to-end speech recognition. It directly we are trained a deep network that maps the speech directly to letter or word sequence. So this system, actually, this one is old-fashioned SR system, but it's still state-of-the-art and used in many real product or services. But so yeah, this SR system has many components: acoustic model, dictionary model, the WFSD. Yeah, it's we are quite complicated, but end-to-end system is much more simple, has much more simple architecture, and so like this figure. So we only have a single deep network and just train the model, and we can decode using this deep network. So the architecture is quite simple. And one more benefit is so we can optimize the deep network entirely. So it's actually it was difficult for the conventional ASR. So yeah, it also has a benefit. So we don't need a pronunciation dictionary or tokenization. So yeah, there are many good things in the end-to-end SR, but the one problem is so we need more data for running more complex mapping. So actually, we don't have a pronunciation dictionary, so we need to so the model needs to learn the complex mapping from character or word to the acoustic, yeah, between their language and acoustic behaviors. Okay, so in this project, we start from the attention-based sequence-to-sequence model for end-to-end speech recognition. And in our case, we also use the CTC part. So this sequence-to-sequence model is originally proposed for the machine translation. So it's quite nice model that can convert any kind of sequences. But in speech recognition, we only need some monotonic relation of input sequence to output sequence. So in this case, so CTC helps to force the monotonic alignment to the encoder of this network. And also we use the CTC for decoding, and also we combine the RNN language model. So this part is quite useful to use the external text data to train the language model, and which improves the performance of the end-to-end SR system. So this is our baseline system at the start point of this workshop. Okay, so CTC is actually very helpful to train the end-to-end model using a small amount of training data. So upper figures shows the alignment between the input and output sequences during training. Actually, so we only use small, very small amount of training data, so we cannot get the correct alignment between the input and output. So model cannot be trained correctly. But with CTC, loss by adding the CTC loss, so we can get the good monotonic alignment even in the early stage of training. So this method is, so CTC is quite helpful for training the end-to-end model using a small amount of data. So here is the baseline results of the hybrid CTC attention approach. So this is a result from the Mandarin telephone speech transcription task. So adding the CTC and language model and some deeper encoder, so we could successfully reduce the word character error rate. So best now, the last year we got the best CTC attention performance is 28%, which is almost comparable with the state-of-the-art setup. So from Kaldi, so here the Kaldi is using, relying on the pronunciation dictionaries. So it's actually very nice result of the end-to-end SR. But so if we use smaller data, like so very famous Wall Street Journal task, which includes 80 hours of training data. So in this case, yeah, of course, CTC language model, and recently we added word language model. Yeah, it's quite helpful to reduce word error rate. And actually this, at that moment, so last year, so this is the best number compared to other end-to-end systems. But the state-of-the-art system achieved 2.6 word error rate. So there is a still big gap between the end-to-end and so state-of-the-art systems for a small amount of training data. So we want to remove this gap in this project. So first approach is a multi-encoder architecture. So just increasing the model parameters is, has no big improvement for a small training data set. So, and easily, so this overfits to the training data. So our multi-encoder approach is combine the different types of encoders. And we hopefully, yeah, so it's a different encoders hopefully capture so diverse acoustic features and hopefully, yeah, get some complementary effect with these multiple encoders. And also we try to control the encoder contribution in the attention by using the attention mechanism. So the basic concept is not so difficult. So combine multiple encoders with a fusion layer, and and we combine these two encoder outputs in the context vector level. Okay. And also we tried the attentional fusion layer. So this means that so we already using the attention mechanism for each encoders, and then so we apply the attention mechanism for which encoder is important. So this means so we compute the final context vector by weighted sum of the context vectors from multiple encoders. So using this kind of architecture here, so beta is attention weight for each encoders. And these attention weights are dynamically determined by decoder state and context vectors. Okay. Yeah, this is also called hierarchical attention. And yeah, this idea is actually originally proposed for multimodal video description and also multimodal machine translation. So this is a kind of extension for the speech recognition encoder. Yeah, in this, so to evaluate this approach, so we use the Vietnamese ASR task, including the 80 hours of the dataset, so it's not so large. Okay, so the baseline architecture is, yeah, BLSTM P encoder. So P means that projection layer. So the BLSTM has a projection layer right after each BLSTM. And we also use a CTC. This is a baseline. And we also use some different encoder based on the VGG, which is a kind of CNN. It has more, say, CNN layers before BLSTM. Okay. So this is a baseline result. So character error rate. Yeah, they are a little bit higher than WSJ, but it's a Babel corpus. It's acoustic condition is not so great. Okay, so here is we apply the multi-encoder architecture. So first, we got some improvements from the single encoder architecture, like this, and yeah. And then, so we also put the CTC for each encoder. So here, first we try to use a shared CTC. So this CTC has the same parameters for the output layers. And so we got further some improvement by adding CTC. And then, so we also tried the different CTC. So we got some further, yeah, nice improvement. Okay. And finally, we added a language model. Yeah, this is actually the impact of language model is very small because RNN is just trained with transcription of the corpus. Okay. Yeah, so in this work, the multi-encoder architecture can provide so substantial improvements. So it's quite nice. And attentional fusion seems to be working better in this framework. And also not sharing the CTC layer is better than the sharing CTC. So yeah, it's good improvement in the low resource end-to-end SR. Okay, and also we try to apply the word-based language model. So here our network has a language model part of the network, so we can train this language model using large text data. So, but so in this architecture, so this one is tightly connected to the attention decoder. So here it is assumed that RNN language model to predict the same units as the decoder network. So if the decoder network predicts the character sequences, so we can only use character-based language model. So it's not good. So if we can use a large amount of training data, so word-based language is definitely better than the character-based language model. So in this work, so we try to use the word-based language model in these networks. So yeah, in the low resource scenarios, actually the amount of paired data is small, but external text data is very large. So it's a quite realistic situation. So in this case, we train the character-based decoder and word-based RNN language model to exploit both benefits of character and word units. So we proposed new types of RNN language model, but it's more related to the decoding technique. So called, we say that it's a look ahead word LM. So in the decoding part, so actually the decoder predicts the character sequence. So we need to define the language model probability based on the character sequence. So here we applied word LM score. Yeah, it's possible to apply the word language model score instead of the character language model scores. But the word LM score is actually can be applied only at the end of words. So it's not great. So it's too late to keep the correct hypothesis in the beam search. So we introduce a look-ahead technique to factorize the word LM scores into characters to apply the score as early as possible. Yeah, I think, yeah, it's, yeah, we actually use tree lexicon representation. So I think, yeah, this is a very old-fashioned ASR, and this kind of technique I actually used in for the speech recognition before WFSD appears. But for RNN language models, so this is quite important, and we can compute the character level probabilities using word-based probabilities based on the look-ahead technique. So yeah, this character-based probability can be computed based on the sum of the future corresponding word and divided. This probability easily computed. So, but one problem is that the sum of the probabilities needs some more computation. But so we could solve the problem of the computation by adding the pre-computed cumulative sum approaches over softmax. So actually this probability can be computed very efficiently. Okay, so we have some good improvement for the WSJ task, including just 80 hours of training data, and we got some improvement by adding the word language model. Yeah, it's not effective. Just adding the word language model is not effective because most of correct hypotheses are pruned during the beam search. But by using the look-ahead word language model, we got the best. We updated the best performance for the WSJ in the end-to-end ASR condition. And finally, we combine with the multi-encoder and word language model on WSJ task. So the baseline is a single encoder plus character language model. So the word error rate is 7.7. And by adding the word language model, we'll go 5.1. And finally, so the combination multi-encoder plus word language model, we got 3.6 word error rate. So it's got much closer to the state of the art. We are still behind the state of the art, but yeah, we got a very nice improvement by using some techniques. Okay. So the second topic is more related to the learning methods for unpaired data. So here we tried the back translation approach and the cycle consistency based training. So, okay. So here, so we use unpaired data. So first approach is back translation. So here, so we assume that, so here we only have a text only data. So, and if we have a nice TTS system, so text-to-speech system, so actually we can generate audio data from the text data. So the problem is solved, so we can get tons of paired data from the text. Yeah, it's really nice. And also the consistency, the other approach is a cycle consistency. So here, so we also use the TTS, but the approach is different. So here we assume only have audio data. And so first we recognize SR, this audio by using the existing SR system and obtain the text data. And then, so we apply the text to speech, and we get audio data. And by computing the cycle consistency loss, so we try to improve the ASR performance. So in this case, we can train the ASR model with only audios. Okay. So in these approaches, so TTS part is quite important. But I'm not TTS specialist. Actually, I'm not sure about the TTS. But so to make a TTS system, actually there are many need to build many components like F0 duration. There are many things. So I think I cannot build this kind of system. But fortunately, so recently we can use the end-to-end TTS system. So it's a kind of it consists of the neural generator and the neural vocoder. It's a free train the audio and text data from scratch, so in the end-to-end fashion. So it's quite nice. So in this approach, research, we decided to use the Tacotron 2. Yeah, I think there is a talk by Yujian this afternoon. So yeah, this is so sequence-to-sequence model that synthesize the speech data from the text. Yeah, I skipped the detailed network architecture, but yeah, it's quite useful, and I can use manage this TTS component. Okay, so the first, so back translation style data augmentation is done like this. So actually, there are some problems. So just applying the TTS system. So synthesizing raw waveform has some, it's actually computationally expensive, and also the generated speech has less speaker variations. So actually, it's not good for training the ASR system. So ASR system needs to accept various characteristics, speeches. But so TTS can generate only specific speakers. Or, quite difficult to generate various speakers' voice. So in this research, so we decided to generate ASR decoder states state sequence, so instead of the raw waveform. So we say that this approach is a text to encoder, so TTE model. So this is the block diagram of our approach. So yeah, in this case, we use a small amount of the paired data, and assuming that we have a larger set of text data. So yeah, first we trained ASR model, encoder and decoder, and TTE model using these paired data. And then, so we trained the ASR model using this paired data and this text data. So if we have a paired data, so we update the model parameters using the conventional, regular cross entropy based loss. But if we don't have audio data, so we only have text data, so first we generate encoder state, SR. And this state sequence is given to fed to the ASR attention and decoder part, and computes the ASR loss to improve the performance. So by doing this alternately, so we got some improvement here. So this is results shows that, so these results are coming from the 100 pairs data in library speech corpus and unpaired data consisting of 360 hours, but we only use the text data. So we evaluated the method with pure attention-based SR and Takotron's TTE model. So the baseline is obtained with only SR model trained using paired data. So by applying the this part, so TT model and joint training, we got some improvement from the baseline. Okay, but compared to the Oracle case, Oracle case means that we have the paired data of 460 hours, so it's actually much better than this result. So we still have a big gap. But so this approach actually works even if we are just only using text data. And also we had another benefit by using text-only data in this approach. So we augmented the data from text to audio. So in that case, so actually the speech recognition system can recognize the unknown words that are not included in the original paired data. So for end-to-end system, it's difficult to add some new word in the system. But by using this approach, so we can, so the end-to-end system can recognize the unknown words, and we can so correctly, some incorrect so error words are recovered by using this approach. Okay, and so the other one is a cycle consistency training. So maybe you know the recently used to train machine translation or image-to-image transformation, like this manner. So okay. So here is an assumption that input, so input sequence is converted to the output domain, and the output sequence is back translated, so reconstructed using these functions. So the assumption is that so if these two models are well trained to good model, so these two so input and reconstructed input should be similar. So we try to reduce this this distance, and it should work to improve the performance of these functions. So in the speech recognition case, actually it's a big challenge. So because machine translation on the image transformation tasks, so the X and Y are actually the same media data, but in speech recognition, so these are speech and text, so much different. We need to handle different type of data. But in this case, so we use ASR and TTS and compute the cycle consistency loss. So we need to consider some problems in this approach. So as a first step, so we try to use the audio-only data to train the ASR model. So here, so also again, the speaker variation is not considered in this approach. And also expensive to synthesize low waveform or spectral features. And also another problem is that text information is used here. So text Y is basically selected by argmax. And actually this function argmax is not differentiable. So we need to think about a better way to train this cycle consistency based model. So again, so approach is to use the text to encoder. So here we implemented the training method like this. So we also use a TTE approach. So here first the ASR part generates the encoder state sequence, and then so decoder produce the ASR hypothesis, and the TTE part encode and decode to reconstruct the ASR encoder state sequence. So we compute the loss between these sequences, and we can backprop the ASR system. So in this case, so we don't have to use full speech synthesis. Yeah, it's actually about 10 times faster. The encoder state has less speaker variation, so this could be nice for training. So it depends on the TTS speaker variation. And this part, so we still have a bottleneck part here, so text, so argmax part, but we used in this project, so we applied expected loss approach to be the so that the function can be differentiable. So we computed the expected TT loss. So here, an end-to-end approach, in this case, so to obtain the expected loss, we need some marginalization all over possible sentences, but we approximate it by just a sampling technique from ASR posterior probability. So this is computed based on this equation. So we can compute the differentiable TT loss. And here the expected TT loss is computed based on the tacotron2 loss, consisting of mean squared error and L1 loss. So by using this approach, so we also got some improvement by using only audio data. So this is baseline, and we got some improvement. But still a big gap to the Oracle results. So we need to work, and I think we can combine the back translation approach and cycle consistency approach, and also we can consider training the TTS simultaneously in this framework. But so at this moment, we got some improvements, and we hope that we can extend this approach for the unpaired data training. Okay, so in these talks, I presented some results from the Jelinek summer workshop. Yeah, okay, and also proposed some method multi-encode architecture, and also we investigated some new learning methods for unpaired data. Yeah, but still difficult to recognize low-resource languages from diverse environments like Babel corpus. We got still 50% error rate. So yeah, some more evaluation is various tasks, including low-resource languages are quite important. And also we want to extend our technique to multilingual unpaired data training. Okay, thank you. So one more thing, I'd like to introduce ESPNet, which is a kind of open source toolkit. This project is led by Shinji, mainly Shinji, and I think this is a quite nice toolkit. And okay, and also I'm asked by some organizers to introduce the Jelinek workshops next year. So they said that we only submit one paper proposal by November 5th. Yeah, I think it's a good workshop, and I recommend you to read or join the workshop. Yeah. Okay, thank you very much.
So we just have a quick question from someone. Sure.
Everything you talked about is in the toolkit? Just curious, is everything you talked about in the toolkit available for use?
So you mean that all the techniques are included in the ESPNet? Yes, still some projects are still ongoing, and not the latest techniques are still not included in the ESPNet, but most of techniques are actually included in the toolkit or will be included very soon.
Thank the speaker again. And let's move to the second